Last day, we have discussed how we can implement the logic of inserting some node or deleting some node from the linked list. By the way, when we talked about the logic, one thing I told you that you can, before you insert or delete something, before you modify the linked list, you must check whether the position is actually correct or not. So if you want to find the position, suppose that you have a linked list something like this, okay, something like this, suppose, and you want to insert something within this linked list, or you want to delete something from this linked list, and if you want to initially check whether the position that you want to delete or where you want to insert is correct or not, in a correct range or not, that means at least you have to know the number of nodes that is presently in the linked list, right? So now how you can get the number of nodes? There is two ways. That means one problem come here, that find number of node of a linked list. So how you can do that? You see, if you have a linked list something like this, you can say there are 3 nodes. And for example, if you have an array, okay, if you have an array, and if I ask you that how many data are there, you will start journey from here and you will go till last and you will check total how many elements are present. So in the same way, basically, I need a counter variable, right? So for example, I can consider the counter variable as say 0 initially, and till end of the linked list, I will keep on counting this number of node using this variable c. So this code is very simple, that while the pointer, obviously you need one pointer which will point this particular node, that is pointed by head, but you will not use head node, you will not this head pointer, because this is the only key that you have in the linked list. That's why what I told you, that always take a extra variable, a temporary variable, say t, which you can change, so that if t goes till last, doesn't matter, the head contain the address of the first node. So that means here you can easily write that while t not equal to null, you will keep on counting c equal to c plus 1, and obviously you have to write t equal to t next. So when this loop will break, loop will break somewhere when t will come somewhere here, what is basically null. So in this situation, t is not null, so count become 1. Then t equal to t next, that means t came here. So t is not pointing here, t was pointing here, t is again not null. So count become 1 plus 1 equal to 2. Again t equal to t next, so t become here, and count become, still t is not null. So again count become 2 plus 1 equal to 3, and then t equal to t next, so t will now point to somewhere in null, and since this condition will be false at that time, so loop will break, and if you print c, you will get the correct value, that is 3, at least with respect to the example. So by this set of, that means before you check whether the position is correct or not in the regarding implementing the insert and delete operation, you can write this particular code every time. But one more thing you can do, you can take this c as a global variable, and whenever you are creating the linked list, or maybe you are inserting some node on the linked list, as soon as you will insert the node or delete some node or create the linked list, you can add, increment this c by 1. That also you can do. So since c is the global variable, in that case, that value of the c will be visible throughout the whole function. And one more thing is that we have a lot of different type of functions that we can see over here, right? For example, one is the function. If I consider, you can consider a function for creating, a function for say insert, a function for delete node from the linked list, a function for display, a function maybe for reverse. So as we will find in now some new problems, for example, the function for count the number of nodes, like this. So as soon as we will find new problems, we can consider that each and every are actually some functions, and which is working on the same linked list. That means now when you are writing a program, you don't know whether insert function will be called first, or create function will be called first, or delete function will be called first, like that, right? So in which particular order this function will get called, you don't know, right? So that's why one suggestion I have, you can do this, like you can keep a switch case, and in each and every case you can call these functions. So you can have a situation something like you have a choice. So we will have a switch case over here, say switch ch, and if it is case 1, then maybe we'll call the create function. So I am writing in an abstract way. Maybe the code will be little bit different, but the logic remains same. If case 2, then maybe we'll call insert function. If case 3, then maybe we'll call say delete function. So in this way, you can call for different cases, you can call different functions over here, and you don't know how many times you can continue this. So you must be in a infinite loop, where you must have a choice for break from the loop, or you can say exit from the infinite loop, right? And here you will have to scan the ch function. Ch, this ch is, it can be an integer variable, it can be character variable, can be anything. It depends upon that you have to write one. I mean, if it is considered, if I consider ch is an integer variable, for example, press 1 for create, press 2 for insert, press 3 for delete, something like that, then you will be something like this. If you consider ch is a character variable, so this one you cannot write in this way, you should write in a single quote. That you know, I think. So it totally depends upon how you are writing program, but the ultimate, I hope you can understand what I am trying to say. Okay, so let's proceed for a new type of linked list. Till now, the linked list that we have seen would look something like this, right? And what specific architecture that we have seen? It's an one-dimensional connection. I mean, sorry, it's a one-directional connection. And if you start jumping from the first linked list, and if you somehow go over here, if you don't have any backup to point this particular node, there is no way to return back from the second node to here, right? Because the connection is one directional. There is no connection from this node to this node. This is not present. But that means, I mean, due to this, maybe in some situation we have a lot of limitations. And I mean, when we write program for insert, delete, or display, or reverse anything, actually we face the problem, because we always have to remember that when I am jumping from the first node to the second node, I must have a backup that is pointing to the first node, so that I can ultimately return back. If required, I can restart my journey from the previous nodes again. This particular limitation has been overcome in a different type of architecture of the linked list that we call doubly linked list. So what a doubly linked list is, the idea of a linked list is not different over here. Only difference is the connection. if you compare the singly and doubly linked list, initially in a singly linked list, we had a situation something like this. Like we have, say, consider 3 nodes in a singly linked list. If I consider, and suppose the address of the nodes are 100, it's 200, and it's 300. And so next part of the first node should contain 200. Next part of the second node should contain 300. Next part of the last node must contain null because this is the last node. So it's a very, trivial thing that already we have seen. And suppose I have some data over here. And we know that since due to I have stored the address of the second node in the next part of the first node, that's why this particular variable can point this node. Similarly, this particular variable can point this node. So this is the architecture of the singly linked list. Now the difference in doubly linked list is a very simple difference. The difference is something like this. Let me draw the same thing for a doubly linked list situation. In a doubly linked list, instead of having these two locations present in a singly linked list, in case of doubly linked list, we have 3 locations. So actually 3 locations means the middle one is the data part, and the left one and right one both contain the address. Right one point the address of the next node, and left one is pointing the address of the previous node. It's something like this. So for each and every node, it will be something like this. And obviously data should be 3 and 7 and 9, fine. And if I assume the same situation, that it's 100, it's 200, and it's 300, you see the right part is actually same thing as the next over here. So it must contain 200, it must contain 300, and it must contain null. So that's why it can point this particular node, and it can point this particular node. And the left one, actually, as I told you, that it will point, basically, it will contain the address of the previous node. That means the left part of this last node should contain 200. The left part of this second node should contain 100. And since this is the first node, there is nothing to point in, before this first node. That's why the left part of the first node will contain also null. So that's why, since I have a point, I have address of the previous nodes over here, that means now I have a facility that the next node can also point its previous nodes. That was not present in case of singly linked list. So you hear the benefit that I will get if by any chance, if you change your head, then also you can come back to the first node. That was not possible over here. For example, if you write, as I know that conventionally it is pointed by head, say it is a head 1. Okay, one variable, and say this is pointed by, say, head 2. Okay, and if I write a situation something like while head 1, say no, head 1 next not equal to null, head 1 equal to head 1 next. If I write this one, what will happen? Due to this particular criteria, this head will traverse till the last node. So ultimately we will find that this node will no more point here. This head will point to the last node, because at the last node, this head next will be equal to null. So null not equal to null will become false. Now, yes, the problem that we will face in case of in this architecture is that when this while loop will break, since head is pointing here, that and the the traversing is in one direction only, that there is no way to return back to the first node. That means you actually lost all the nodes in the linked list. But if you write say a while loop in this situation, same thing, basically instead of while head 1 I will write head 2. So if I write while head 2 head to next not equal to null, and same thing, head equal to head to equal to head to next. So what will happen? We know that in this case also this head to will no more point this particular node, head to will now point this particular node at the end of this particular loop. But the facility that I have in this situation is that I have a way to go back to the previous nodes. So that means here, after writing this particular loop, if I write again a loop something like while head, suppose that just a minute, if we write say head priv. What is priv? Priv is the variable name that is actually storing the address of the previous nodes, just like what we have next over here. That's why one more variable definitely I require to store the address over here. So I'm considering that is a priv. The variable name is priv. So head priv not equal to null. You can write head 2. Sorry, it's head 2. Head 2 equal to head 2 priv. So what will happen? Head was pointing here, fine. Now head 2 priv. Right now head 2 priv is this one, which is obviously not null. So head 2 equal to head 2 priv. That means now head 2 will point somewhere over here. Right. And then again this priv will not null. So ultimately after executing the second loop, what you will see that head 2 will ultimately reach wherever it was previously. So that means the problem that we had, that every time we had to remember that I have to hold the address of the first node always. I mean, if I cannot hold, I will lose. I may have the problem that we are facing, that every time we have to remember the address of the first node in the singly linked list. The same thing is not happening in case of doubly linked list. That is the benefit that we will get. But other than this, everything what you have seen in case of insert operation, delete operation, in create operation, everything is same. Just one thing you have to remember, that when you will create a linked list, for example, when you have created the linked list for a singly linked list case, what you have done, you have connected the current last node of the linked list with the newly created node only. That's all. But here, not only connection should be towards right, connection should be from the new node to the last node also. And that is the thing you have to, that is the extra thing that you have to think, remember or keep in mind. For example, that means if I consider how the node of this particular doubly linked list will look like, what we can write the node, how we can express the node with respect to code. So obviously I need a structure, right? So basically I can again write a node as a struct node, and within this I can write say int data, which will hold some value as some variable, some value as a data part. And in this case I need 2 pointers. In case of singly linked list, we had only next. So we had something like struct node pointer next. That's all. So here, you had only these 2 parts in case of singly linked list node type. But in case of doubly linked list, what we have, we will need one more variable of the same type, because it is going to point the same type of node, but the direction is just opposite. So I can consider the variable name as priv, so that you can easily realize that what is the exact functionality of the variable. So this is the, you can say the structure declaration for the node of a doubly linked list, right? Now, if you are able to memorize or remember or recall the way we have inserted, we have created a singly linked list, you will see the way is same. So that means I can say that I will have a main function over here. I will have a main function over here. And from in this place, I will call a create function, right? So as we have seen in case of singly linked list, so I can call a create function having head as a head as the pointer pointing to the first node of a linked list, and obviously head should be equal to null. We should declare head as null. So struct node pointer head equal to null, right? So, and this head will be called, as we have seen in case of singly linked list, it is same. So I'm not going in detail of this way how the head will be called, that you know. And this is obviously not only once the create function will be called. Maybe multiple times the create function can be called. So there is two way. One is you can write within a for loop, and another is that we have discussed over here in this case, like this, that you have called the create function somewhere in a case, and since it is within a loop, that means after some execute particular case, again you will have an option to choose one more case or maybe the same case. So if you want to create a function, create a linked list with say 5 nodes, you can choose case 1 say 5 times, right? So now in case of create function, in the create function, I'm not going detail of the what we have over here and what will be the return type over here. Everything remains same. So I'm not going in detail of that. You can understand this thing, I think. And you try to do it in your home so that your knowledge will be more enhanced. But one thing, the thing that is difference over here, only those part I will actually write. So for example, the logic is same, that you have to check that whether you are calling the create function first time or not, and that is the only way you can do. You can check the content of head, because for the first time head will be null, but for the second time onwards it will not remain null. It will point to some valid node. So you can say that if head is equal to null, that means first time. So you will call say variable p equal to say create node function, create underscore node function, which will return a node, right? Which will return a node in pointing to p, and this one it will return p. That's all. And if it is an else part, then what to do? We have to, in a similar way, you have to go till last, right? So that means again you can write a loop over here, that while you can say that say p next not equal to null, p equal to p next. So p is basically the first node that should point. So your p should be initialized by head. And what is head? Head is actually present over here. You should write here struct node pointer head. Don't mix up the head of this and head of this. This head is local variable within main, and this head is local variable within create. But since whatever you are sending through this head actually accepting by the same variable name head, but this head is actually this head, and this head actually the content is same, but the you can say, but the address of this head variable and address of this head variable obviously not same. Anyway, so after this loop end, when the loop will execute, and at the end of the loop, what will happen? P will point to the last node, and you will just have to connect this P with the newly created node. By the way, since already, okay, I have to write this code again over here. So you must write this particular line not only here, but also over here before writing this one. By the way, since we have used P over here, so I should not write P. Here you can write Q, for example, or maybe some other variable, but not the same variable, obviously. So ultimately, at the end of the loop, what will happen? PQ is pointing to the last node, and P is pointing the newly created node. So the situation is something like you have a node, something like this. You have a node. So initially, when this node will get created, at the first time, you don't know whether this is the first node or the last node or what is the situation. So that means when you will create the node, you have this three part, right? And you will put some variable over here. Say, for example, some value is 3. And you don't know what is the status of the newly created, already created linked list, whether there is any linked list to create, to connect with or not. Maybe this particular node is the first node of the linked list. So that means at the time of creation of the node, you must write this as a null as well as this as a null. So that means when you will write the create node function, in the create node function, say create underscore node, and here obviously you have to write some struct node pointer, that struct node pointer. So this part actually common, what we have seen in case of singly linked list. If you have already seen singly linked list, you can easily understand what I'm trying to say. So here you need a variable where you will basically, with respect to that variable, you will basically create the dynamically allocate the memory for the newly node. So that may be say R. So R equal to something, then malloc. So everything is common, that you know this. And what you will do, your job is to initialize R next equal to null, and this part we have already seen in case of singly linked list. But what is left is you have to write R prev equal to null also. Because you don't know whether the node is the first node of the node. Because if it is the first node, then there will be nothing before this. In that case, it should be null. And if it is not the first node, maybe second or third, in that case, automatically that will be connected with the last node of the already created linked list, where somewhere over here. Because after executing this loop, we can understand one thing, that Q will point to the last node of the linked list. So for example, I have a situation something like this. I have a situation, say I have 3 nodes over here. Okay. And say it's a doubly linked list. So I'm not going in detail writing each and every addresses over here. So for example, they will point, somehow they are pointing, if I consider they are pointing correctly, and this is your head. And we started Q over here because we started Q from head. Sorry, so it should be Q also, right? So Q equal to head, and while Q next not equal to null, Q equal to Q next. So when the while loop will break, this Q is no more pointing here, Q is pointing somewhere here, right? And your newly created node is this. That actually happened due to execution of this particular line presented in this part also, right? I'm not rewriting the same statement, you can understand this. So due to this execution of this statement, already there is a newly created node which is pointed by P, because I have written P equal to, fine, and Q is pointing to the last node of the linked list. And what is your job? And your current situation of this node P is, this is also null, and this is also null, right? It contains null, it contains null. And now what to do? You have to connect this, Q node with the P node. So what you will write? You will basically write a very simple statement. I think you can easily understand. You will write Q next equal to P, so that what will happen? The next part will contain the address of this node, so it can point this one, but here it doesn't end. This is what I'm saying, because this particular part already was there in terms of singly linked list. We have seen that. But since this is doubly linked list, I have one more extra job that I have to have. That is, somehow I have to connect this particular part also. And how I can do this? I can access the brief part of P, where I will write the address of this node, which is holded in Q. So basically, what I will write, after writing Q next equal to P, I also write P brief equal to Q. So this is the extra thing that we have in the doubly linked list. You see, if you go through the logic of implementing a doubly linked list, you will see this part is same what we have in singly linked list. This part is, all this part up to this part is same as we have in singly linked list. Only new is this part, right? And in this case also, you can see everything is same as we have seen till this part is same. Only new thing is this. So that's why you can easily understand how close logic that we have in case of creation of a singly linked list and doubly linked list, right? So I don't think you will have any trouble for creating a doubly linked list if you have a good idea of creating a singly linked list too. So do one thing, it's my suggestion that you try to implement a doubly linked list also in a separate program, and try to follow this type of approach, because in case of doubly linked list also you'll have a insertion logic, deletion logic, and everything. So now see, if I consider the insertion logic of doubly linked list, you see, since the idea is only different in 1 or 2 or 3 lines only, that means in case of inserting a node in a linked list also have the same thing, same impact. So that means if I go through the insertion logic of doubly linked list, insert in doubly linked list, so we have a doubly linked list something like this. A situation is something like this. And obviously this is null, this part. So 100, 200, 300, and it will be 200, it will be 100, it will be 300, it will be 200, and this part will be null, and this part will be null also. So it will point this node, it will point this node, this will point this node, this will point this node, and this is pointed by head, conventionally a variable head. So this is the situation, and what you have to do now, you have to insert. So in case of inserting a node in a singly linked list, we have seen that I have only checking inserting at the beginning or inserting another part is sufficient. So if the position is equal to 1, the position can be 1, or the position variable can be value some value p, maybe 2, maybe 3, maybe 4, and you can easily check that whether the position is correct or not. That is same as singly linked list. So I think I should not repeat again that how to check all this. But one thing, if I assume that position equal to 1, so that means if position equal to 1, then what to do? The first step is that create a new node, and assume that I'm assuming It's pointed by for example T1. Okay, so that means I have created a new node over here. Suppose I have created a new node over here. Okay, and since I have created a new node, the creating new node is the same something like we have already discussed over here, right? The same function. And that's why as soon as I have created a new node, the prev and next is already null. So I can say that the two part present over here, some data is present, maybe say 10. Okay. Oh, by the way, I have not written data anything. So like 3, 2, 8 or something like this. And maybe the value 10 is here. And initially it both contain null, right? So I mean, it's a scattered node. It's not still connected. So after doing this, what to do? You have to, what is the next step? The next step is, what you can say, right now it is pointed by some variable, say T1, as we have seen, right? So it's pointed by T1, we have already assumed that. So, and it is pointed by head. So basically what to do, you have to connect this particular one with head, T with head and head with T also. So that means what I will write, I will simply write T1 next equal to head. And in other side, also I should write head prev equal to T1. So only these two statements will help you to connect this node with this node and this node with this node. Now, when you are connecting, that means this null will get replaced by the address of this node, that is 100. So now it will become 100, right? Null will not present over here, but null will present over here because this is going to be the first node. Now, since this is going to be the first node, after inserting this one, this head should not point over here. That means now I should update my head. So I can say that now head will be equal to T1, right? So as soon as this statement will execute, the head will no more point to the first node. That means now head will not point here, rather head will now point this newly created node. And you see, if you start journey from the first node of the linked list for displaying the content of the linked list, obviously you will start from here. So initially you had, if you print, you were 3, 2 and 8. And now if you print the content on the linked list, it will show 10, 3, 2 and 8. As if 10 has been added in the, 10 has been inserted at the beginning of the linked list. Something like this. So you see, if you go through the difference between the inserting logic with respect to the singly linked list, you will have only one difference. That is this one, I think. Right? So that means, I hope you can easily understand that why singly linked list was so important, because the logic of the each and every logic is hidden within singly linked list concept. And based on that singly linked list concept, the modification came. And this modification only on 1 or 2 or 3 lines. That's all. So that means the person who have idea of singly linked list can implement any linked list. So that's why I'm telling you that you must be very much careful when you will learn singly linked list. You must implement each and every function somehow in the singly linked list, so that if you're able to do that, just adding 2 or 3 more lines, you can convert your singly linked list to doubly linked list. That's all. Okay. So what we have seen this is actually for position 1. Now for else part, if I consider the else part, and somehow if I consider that the position is correct, okay, if I consider the position that you inserted is correct, for example, this is the newly created node which is connected. So ultimately now in the doubly linked list I have 4 nodes. That means I can insert a new node between 1 and 2 or 2 and 3 or 3 and 4, right? Or maybe after 4. So that means your position may be 2 to 5. Any value is correct value. But if your considered position will be equal to 6, that is not possible because already you have only 4 nodes. You can maximum insert at the 5th position, but not greater than 5th. Anyway, so already we have discussed that how you can check whether the position is correct or not in case of singly linked list, which logic is basically same for doubly linked list also. So I don't think that is going to discussing the same logic will make any sense in this particular lecture. So that's why I'm skipping that how you will find that position is correct or not. Assume that you are in correct position and take any situation. For example, I want to insert say in between position 2 and 3. So somewhere like this. Okay. So that means again the first step is that you have to create the node. So create the node, create a new node which is pointed by T, pointed by say P, not P. I have already P over here. So pointed by T1. Okay. So pointed by T1. And what to do now here? So suppose the position according to the position given from the user, it will be something like in this, in between 2 and 3 I want to insert. So your newly created node is present somewhere here. Okay. And maybe some value is present, obviously say 12. And obviously this is null and this is null also, right? So initially this is not still connected with the newly created node. So now what to do? As we have seen in case of singly linked list insertion, that if you want to connect, if you want to place this newly created node between 2 and 3, somehow if you have to keep a pointer to this node so that you can access the next part, because this next part should contain the address of this, and also you should point this node whose previous part should be accessed to connect this part, right? So that means how we can do this? We have seen already, in the previous lecture that there is you can easily write a logic that you can start with I equal to 1, and you can write that while I less than equal to pause minus 2, you will just do one thing. You will just traverse with a pointer. Say for example R. For example R. So R was suppose initially pointing here. So you will just traverse R equal to R next. That's all. So when this while loop will break, what will happen? R is pointing somewhere here. Right. So in this situation, pause was 3. In this example, pause is equal to 3. So 3 minus 2 equal to 1. Right. And I was 1. So 1 lesser equal to 1. True. R become R next. So now R will come here. And then I will be incremented by 1. Right. So that means I will become 2. So 2 lesser than equal to 1 will be false and loop will break. And you see you are pointing here. So by logic you are correct. And then what to do? So you have pointed this node, but there is no pointer pointing here. So that means I need one more pointer. That means somehow I have to implement this particular logic that I have written over here, somewhere over here in step 2, right? And then what to do? We need one more pointer over here that will point this node. So you can write say S equal to R next, where S, if you have to declare S obviously as a struct node pointer, because it is going to point a structure struct node of some struct node in the linked list. So that means now S is pointing here. So if you are able to do this, your 80% and maybe 90% job is completed. Now its only job is to connect properly. Now what to do? If you want to place this newly created node in between this R and S, what to do? You have to just replace the address 200 by the address of this newly created node, which is pointed by T1, right? So what you can write? You can easily write now in this 4th step, you can easily write that R next equal to T1. So as soon as this particular statement will execute, what will happen? this particular line will get connected, and that means this 200 will get replaced by address of this node, and suppose address of this node is say 400. Okay, so that means this 400 will come here. By the way, this null should not be present over here also, because after connecting this one with this, if I assume that address of this is 500, it should become 500. Okay, so this was the first situation in case of pos equal to 1. So now we are discussing for other positions. So 400 came here, fine. Now it can point here. Now one more thing is left, that is connecting this newly created node to R. So that means in a similar way, you have to write T1 priv equal to R, right? So that this particular node now point this node, right? Now, since already now this node is pointing this, that means this connection has terminated. There is no connection over here. Okay. Now, similarly, this part I have connected, but still I have not connected this two. That means what I have to do? I have to write S. Similarly, S is pointing here. S is the actually next node of this newly created node. So it should be S priv should be address of this node. That means you should write S priv equal to T1 and as well as T1 next equal to S, right? So if you are able to, if you write this two statement, next two statement, what will happen? This particular connection will get connected, as well as we will have a connection over here also. So as soon as this will connected, this termination will be, this is also terminated. So that means ultimately the modification of the linked list becomes something like this. There is no connection over here, and you see now as if this particular newly created node has been inserted in between second and third node, right? So, and it has been successfully done. So if you compare this insert operation for the else part with respect to the insert operation in case of singly linked list, you will see here I have only difference of two lines of this containing priv operation. This part was there in case of single linked list. Obviously, this part will be there because these are all forward connection. This forward connection was there in case of inserting a node in a single linked list also. So the backward connection only the difference. So now I think you can easily understand how much easy implementing a doubly linked list is, right? So if the insert operation is clear to you, I don't think I should repeat the delete operation because it is same. Only thing you must remember that whenever deleting a node, you must delete the connection from both ends. Because in previous case, I was holding you, but you were not holding me. That means when I am terminating the connection between I and you, basically I am terminating only one connection because there is only one connection. But in case of, if I compare the situation in case of doubly linked list, I am not holding you, you are also holding me. So that means if I want to terminate the connection between I and you, I have to terminate two connections, right? So that means if I go for the delete operation, if I go for delete operation of doubly linked list, in the similar way I have two cases. If pos equal to 1, what to do? You see, the situation is something like this. So the total number of nodes is now present 1, 2, 3, 4, 5. Fine, no problem. Now I want to delete the first node, position equal to 1. So if you want to delete the first node, obviously after deleting this one, the next second one will be the head. That is fine. But one thing is that you must have null over here in the prev part of the second node. You don't need to think about what we have over here in the next part, because I'm going to vanish this particular node using free function. If I free the memory allocation for this node, automatically there will be no existence of any null or anything. But important is deleting this, keeping null this part. So that means if pos equal to 1, the first thing is that you have to change your head. You can easily do that because you have a forward connection from the first to second, and that means you can easily say that by the way, before forwarding to head, you must write that p equal to head, or maybe say t1 equal to head. T1 is a pointer that is temporarily pointing this node. Why? Because I want to free this location. If you want to free the location, you have to point this particular location by some pointer. That's why I have kept t1. Fine. And then what I can do, I can write head equal to head next. So then what will happen now? So this head will no more point here. Now head will point this node after executing this particular line. And then what you can do? You can simply say that now head prev equal to null. So you are writing head prev equal to null as if, what does it mean? It means that you are terminating this connection. Right. And then if you write free T1, what does it mean? Mean you will dynamically delete the entire memory location pointed by T1. That means it will basically vanish the whole node. And if it is vanishes, there is the existence of 100 or null anything. So it is not going to point this one, it is not going to point this one. The whole thing will be vanished, something like this. So now it's done. Your first node has been deleted. It's very easy, I think. You can easily realize it that it's going to be very easy to delete the first node. But if it is in else, then what to do? If it is in else, then what to do? Obviously, we have already seen that, for example, suppose now I want to delete this node. For example, let's just delete this part so that you will not get confused with this particular variable names. So forget about these variable names for time being. So the situation is something like, now it is null, and obviously it is 400 and everything. Okay, fine. It is not even null. This will be some valid address, right? It should contain some valid address. It should contain null. It contain valid address, that is 400. So it should contain what? It should contain address of this node, that is 100, and it should contain address of this node, that is 200, right? And okay, fine. So other things are okay, fine. So now suppose that I want to delete the third node. If you want to delete this third node, what does it mean? If after deleting the third node, that means the second node will directly interact with the fourth node, right? Now see, you can easily do that. Since we have a facility to go back through some, backward connection, that means now there is no need to hold the address of the current node before jumping to the next node, because you can easily go back. So that means, since it is third position, that means, you see, you will start with this position. I need a pointer that will point this node. Suppose the pointer is initially T1. Okay. So suppose T1 is pointing this node. Fine. And then what to do? You can easily see that somehow I have to reach to this node because I want to delete this. And if you want to reach over here, you can say that do one thing. By the way, you can reach over here also, or maybe somewhere over here. It's better you can reach over here. Now see, if you want to reach to the previous node of which one you want to delete, that means you have to actually go through the same, the same loop that is written over here, right? So here pos equal to 2. Now pos equal to 3 again. Yes. Here also pos equal to 3 for deleting in the third node. Pos equal to 3. And so 3 minus 2 is 1. So 1 lesser equal to 1. So easily I can understand this particular loop will run once, and that I require. Because now that means the loop that I will write over here will be what? I will write simple loop, same thing over here. That means I will write I equal to 1, and while I less than equal to pos minus 2, just I will write T1 equal to T1 next. That's all, right? And here this pos is value of pos is what? Value of pos is 3 in my example, because I am trying to delete the third node. Fine. And you see 3 minus 2 is equal to 1. So I equal to 1. 1 lesser equal to 1. That means I can easily understand that loop will run only once. So, and from the example also I can see that it's, yes, it is required that my T1 should point here, and running once this T1 will come here, right? And that I require. So I am correct. I am technically, well, logically till now I am correct. So let's see now what will happen. Now what to do? From this example I can easily see that if I want to delete this particular node, that means the connection of this next part of this node should actually be somewhere in the next part of actually next to next of the node where I am pointing right now, right? So that means already we have seen that T next this particular situation we have already seen. So I think now you can easily do that over here also. So that means what I can write? I can write here that T1 next equal to what? You see, T1 next means this part, because T1 is pointing here. So T1 next should contain T1 next right now, that is 200. Who's next? 300, that one. Because 300 should be present over here. So that means you can easily say that T1 next should be T1 next. But let me do one more thing. If you are able to do that, okay. So I can write T1 next. I'm sorry. Okay. And what will happen when this particular code will get executed? This 200 will get replaced by the next value of the next node of present where of this particular node, that is 300. So this 200 will get replaced by the value 300. Fine. As soon as this will replace by 300, this connection will vanish. Fine. And what will happen? Now this is pointing to this node directly because 300 is the node of this. So that means now I can connect this node directly. I mean, if I write T1 equal to T1 next, I will directly go over here without bypassing here, right? So let's go, because I have to go over there, because I have to change the pre part of this node so that it can point directly this node, right? So that means somehow I should use one more variable, say T2 equal to, you can write T1 next now. So that means now after executing this first line, T1 next means the last node in the linked list, this one, right? So that means now T2 will point this node. So if I am able to point this node by a pointer, I can easily access the pre part of the node. So now what I will write? I will simply write T2 equal to T2. I'm sorry, not T2 equal to. I can easily write T2 triv equal to T1, because T1 is pointing this node. So this prev 200 now will gets replaced by the value 400, because T1 is pointing the node of address 400. So it will contain 400. As soon as it will contain 400, this connection will get terminated. And I can point this node. So you see, now the connection has been established directly from this node to this node. Fine, no problem. But still there is one problem. The problem is that since you have connected these two nodes and there is no node which is connecting this node, you can never delete this node, which was a benefit for dynamic memory allocation. That means before connecting this node, you must point this node in some another value pointer. So for example, that means before proceed for terminating the connections between this node with this node or this last node with this node, I must point take this node by a pointer. So and where I can do that? I can do that easily somewhere over here at the very beginning. So what you can do, you can consider say T3 equal to T1 next over here. You see, I'm writing T1 next. Why? The reason is that I have still not terminated the connection between this node and this node. And this connection will be terminated as soon as this particular line will get executed. But that's why I have written before this line, T3 equal to T1 next. That means so that this can point, T3 can point this node. And after that, if you write these statements, there is no problem. T3 is still pointing the node that I have deleted. So now you can easily write free T3. That's all. So what will happen? The entire node will vanish. And if the node vanishes, there is no, evidence of this connection. And you see, we have actually connected we have actually deleted what the particular node that we are actually trying to delete. Now still, I can minimize this particular two lines. You see, in case of singly linked, we have seen one thing, that if you write T2 equal to T1 next and T3 equal to T2 next, these two statements you can merge to write T3 equal to T1 next. We have seen this, right? Even I have written here also. Similarly, we can merge these two statements also. What is written? Let's write over here. So let's erase this part. I've written here, it was given so here it was given T2 equal to T1 next. Fine. Then T2 prev equal to T1, I've written. Now what is T2? T2 means T1 next. So that means this particular two line, if I merge, I can write T1 next prev equal to T1 directly. Because this is the part of T2 that was there in the second line. So instead of T2, I have directly written T1 next. You can do that. So that means this one line, instead of writing this two line, I can write a single line also over here. Now, if you think that it becomes a little bit complex to realize it. At the very beginning, as a beginner, obviously, maybe you will face some, you will face a little bit difficulty to realize what does it mean. You can avoid this and try a very simple statement. But as you will go expert in this data structure subject or writing program, I think this particular line will not, will not be very difficult to write or realize for the next other programs. Okay. So if this is now clear to you, we can proceed more with one more type of linked list that is again very easy. That is what we call circular linked list. Circular linked list. Circular linked list. Circular means you can easily understand. Circular means you can easily understand that they are connected in a circle. So what does it mean? It means something like you can assume in this way, like you have a node over here. So let's take an example. Suppose we have a node here and have a node here. And suppose node here. And some value is present over here. I'm not going in bold a lot of details over here. Say 10, 12, 7, 3. Okay, so if I consider it is a singly linked list, in case of singly linked list, what we have seen. So let's take, okay, let's make it clearly. So 300, and suppose it is 400, and so if I consider it is a singly linked list, here I should have 200, here I should have 300, here I should have 400, right? And then this one, and this one, right? And here we had null in case of singly linked list, but in case of circular, it means they will be in a circle. So that means there is no null, no last node, no first node, nothing. So that means in last node of the linked list should contain address of the first node. So that means here I should contain 100. So that means it is as if pointing this particular node. So it is in a circular fashion, right? Now it can be in a both direction also. For example, instead of writing, if you consider that each and every node has 2 pointers like prev and next, like doubly linked list. So just assume that I have one more place over here, right? One more place over here, and this particular node will contain 100. That's why it is pointing this node. This should contain 200, pointing this node. This particular node contain 300, fine, pointing this node. And what about this? This particular node will contain the address of the last node, that is 400. So that means what will happen? That means this node will point to this node, something like this. So that is the difference only. But you see, ultimately at the time of creating, I will have a little bit difference with respect to creating a circular linked list. What is the difference? Difference is that the circular fashion, I mean, if you make a linked list in circular fashion, you cannot say that you will insert all the nodes and then you will connect the next part of the last node with the first node. You cannot say that because you don't know where it ends as a programmer. You don't know how many nodes will get inserted, right? So what to do? That means each and every time when you are inserting something at the end, you must connect, update that one. So how to do this? Let's do one thing. Let's take that. Means one thing we can easily say that circular linked list can be implemented in 2 different ways. One in singly, one in doubly way, right? So if you are understanding singly way, I think doubly way, I think pretty easy for you, right? So just one thing, you have to think about the other direction pointer. That's the only thing difference. So there is no other difference, right? So if I consider about circular linked list in a circular singly linked list, so in case of insertion, I mean in case of creating a node, what you can do, say I will have obviously main function from where I will call. Obviously I need a head node because some among, I mean if I consider there is a lot of points over here, lot of points are here, and they are in this fashion, among all these points must be one will be head from where I will start. So they definitely. So that's why obviously we'll have a create same way like head. And in the create function, the first step is obviously create a new node. You see, in the previous cases, we have done create a new node somewhere. Where I've written this? Here. I have created the node within the if. That's why I have to repeat in the else part. So since I have to create a node, that's why you can do one thing. Instead of writing create node in both places, in if and else both, you can keep this, this particular line even before if statement, so that you will not need to repeat the same statement both if and else part, right? And that is what I have done over here actually. I've created a new node. I have not even started the condition that whether first time or next time. Okay, so created a new node, fine. So assume that I have created a new node, fine. So since we are considering it is a singly linked list in circular fashion, that means I have two parts. And obviously there is a create node function call for this, and that already you know. So I'm assuming that you can understand that some create node will be created, which will be pointed by some variable, say t, and some value will be present over here, for example, say 10, and it contain null right now, but it should not contain null. What it should contain? Initially, if I consider this is the only node in the linked list, since it is a circular linked list, it should point itself, right? So that means there is only one difference in case of creating a node in the circular linked list fashion, is that when you will write the create node function, if you write the create node function for a circular linked list, say assume that I have written p equal to something malloc. I'm not going detail of this, right? So p is the new node that is pointing this one. So it should be t, as I have written t, fine. And then what should write? We are habituated to write t next equal to head. T next equal to null. We are habituated to write t next equal to null. But here you should write t next equal to p itself. It is something like a pointing to itself, because you don't know after creating the first node whether there will be any more node or not in the linked list. If there is no more node, then it should point itself according to circular fashion. So that means it should not contain null, rather it should contain address of its own node. If I assume that the address of this node is 100, it should contain 100. But if I add any more node later, then according to that some modification I have to do. That I'm coming very soon. So now if I after creating this node, you can obviously check that if the head is equal to null or not. It's already you have done many times, so you can easily understand what you have to write in if. And then in else part, what to do? In else part means assume that a situation that you have a number of nodes in the linked list. So in the else part means you have already some amount of node in the linked list. That may be one or maybe more than one. So just for understanding how the linked list will have a circular fashion in that situation, let's assume that you have say 2 or 3 nodes. So I'm drawing the nodes accordingly. Okay. So assume that we have 2 or 3 nodes in the linked list already, and which is already in a circular fashion. So the situation is something like 100, 200, 300. It's should contain 200. It's a 12. It contains 300, and say it's 8. It should contain 100. Right. So that it is pointing this one. This is pointing this one, and this is pointing this one, like something like this. And in this situation, a new node you have created, and you have coming else part. So it's something like a new node has been created somewhere over here. It is represented by a new node over here, right? So what is the task? You have to connect this particular part first thing. So you should terminate this particular line, and then you should have a feedback path from the last node with the first node. Fine. So, and obviously I know that this is pointed by head always. There is a variable head which is pointing this node. Fine. So what to do? You see, as we have seen that the first step is that reach to last node of the linked list. It's a very, first step that already we have discussed many times. We have seen over here also. For example, somewhere, yes, over here we have seen. So this is there. And then what to do? So after reaching the last node, I can assume that there is a pointer which is pointing the last node. For example, T. Yes, for example, T. For example, P. Because T is pointing a newly created node, as we have seen. So T is not pointing here. Forget about T over here, right? So I assume that I took a temporary variable P, which started from head, and at the end it stopped. But here I have a little bit change. Change is that in case of previous cases, you have written for inserting, storing at last, you have written that while obviously you initialize P by head, while P next not equal to null, P equal to P next. These particular things we have done, even in singly linked list and doubly linked list also. You see, we have done this. Q next not equal to null, where you started from head. Fine. But the problem that I will face over here is that this particular criteria, in case of a circular linked list, will lead to an infinite loop. Because according to the logic of circular linked list, there is no space for having a null at the next part. So always next part will remain not null, and your P will keep on circulating in between 3 nodes, because P will start here, P next not null, come here, then P next not null, come in the 3rd node, then again P next not null, now go to the 1st node again, and it will go on. It will never end. So what to write? Obviously you cannot write null over here. What you can write? You see, you can write one thing, that while you will not able to see the address of the 1st node again in the next part, till then you can traverse. So that means in case of writing the traverse till the last node of the linked list, in case of circular fashion, you should not write not equal to null, rather you should write not equal to head. because head is the only variable which contains the address of the first node. So anyway, so that means after executing this loop correctly, we can think one thing, that okay, somehow your P is pointing to the last node of the linked list, current linked list, and this connection is still not established. So what to do? Now it's going to be very easy, right? So you will just write one thing. What you will write? You will simply write P next equal to T, and then you will write T next equal to head. That's all. Because if you write T next equal to head, it means the next part of the T will contain this 100, because head contain 100, head pointing 100. So this connection will get terminated, obviously, because you have written P next equal to T. So this connection will get terminated. The connection from this P to T will get established, and due to T next equal to head, this particular line, what will happen? A connection between this node till the to the first node will get established. And in this way, you see, we have discussed this situation with respect to 3 nodes. If it is possible for 3, it can possible for 1 also. So that means from the else part, due to this particular line, some combination of this if, once, and else for other cases, automatically you will see a circular linked list with respect to in circular singly linked list will be automatically created. It is my suggestion that all of you try to implement the code for doubly linked list as well as code for circular linked list, but you can try the insert operation and delete operation for circular linked list also for your for enhancement of your knowledge. In case of inserting and delete operation also, it's same as we have seen in case of single linked list. But always remember one thing, that in case of circular linked list, the last node doesn't have null. Last node next part doesn't contain null. It should contain address of the head. So when you will change or add or modify something or maybe delete something from the last node, you must remember that if you insert something in the last node, you have already done this. If you delete something of the last, delete the last node, then you must remember that the previous node, the second last node, the next part of the second last node should contain now the address of the head. So that you should be ensured before you delete the last node. Okay. So this is actually all about the basic idea of a linked list that we have discussed. We will in future, in near future, we will see various application of linked list. We will actually work with linked list in various situations. We will see that. So before doing experiment on all those, I think you must have a very crystal clear concept on this linked list. That's why again I am telling you, you please implement it, and if you do have a problem, then you can contact me over the internet. Okay. Now, so we can stop the linked list part over here for today. We will see the application of linked list in after going through some other concept in the data structure. Then we will come back to the linked list again. Okay. Next day we will start a totally different part of the data structure, that is part of the sorting algorithm. Okay. We can stop our class for today over here. We can see in the next day we start the part of sorting algorithm from the next day onwards. And then, so thank you. Bye.